When we talk about modern military systems, two ideas quietly decide success or failure long before impact ever happens: maneuverability and guidance. These are the invisible forces that determine whether a missile hits its target, whether an aircraft survives hostile airspace, or whether a defensive system can react in time. They are not just technical features, they are the language through which modern warfare is written. Maneuverability is, at its core, the ability of a platform to change its path in response to threats, targets, or mission requirements. In early weapon systems, movement was largely predictable. Rockets flew along simple ballistic arcs, aircraft relied on pilot skill alone, and naval weapons followed fixed courses once launched. As countermeasures improved, predictability became a weakness. Maneuverability emerged as a solution to this problem, allowing systems to adapt in real time rather than follow a single, easily anticipated path. In aerial platforms, maneuverability begins with aerodynamics. Wing shape, control surfaces, thrust-to-weight ratio, and structural strength all define how sharply and how quickly an aircraft or missile can turn. High maneuverability allows a fighter aircraft to outturn an opponent in close combat, while for missiles it means the ability to chase agile targets that attempt to evade interception. Modern designs often sacrifice simplicity for performance, using unstable aerodynamic configurations that rely on constant computer correction to remain controllable. This is where guidance systems become inseparable from maneuverability. A highly maneuverable system without precise guidance is chaotic and ineffective. Guidance provides the decision-making logic that tells a platform when and how to maneuver. It processes sensor data, predicts future positions, and issues commands to control surfaces, thrust vectoring systems, or internal actuators. Together, maneuverability provides the physical capability, and guidance provides the intelligence. Guidance systems have evolved through several major stages. The earliest were command-guided systems, where a human operator tracked both the weapon and the target, sending corrective commands manually. These systems required line of sight and constant operator attention, making them vulnerable to jamming, human error, and battlefield chaos. While limited, they introduced the idea that a weapon's path could be adjusted after launch. The next major leap came with inertial guidance. By using gyroscopes and accelerometers, a system could calculate its position and velocity without relying on external signals. Inertial guidance brought autonomy. Missiles no longer needed constant input from an operator, and aircraft could navigate precisely even in poor visibility or electronic warfare environments. The limitation, however, was drift. Small errors accumulated over time, reducing accuracy over long distances. To solve this, inertial systems were paired with external references. Satellite navigation dramatically changed the landscape by providing continuous position updates. With satellite guidance, long-range precision became routine rather than exceptional. Maneuverability gained a new purpose. Instead of simply avoiding threats, systems could make fine adjustments throughout flight to ensure pinpoint accuracy at the end of their trajectory. Terminal guidance further refined this process. In the final phase of flight, sensors such as radar, infrared, or optical seekers take over. These sensors lock onto the target itself, allowing last-second maneuvers to compensate for movement or deception. This is especially important against mobile or evasive targets. A maneuverable platform with terminal guidance can correct its path aggressively, making interception or evasion far more difficult. One of the most significant developments linking maneuverability and guidance is thrust vectoring. Instead of relying solely on aerodynamic surfaces, thrust vectoring allows engines to redirect exhaust flow, changing direction almost instantly. This enables extreme maneuvers even at low speeds or high altitudes where control surfaces are less effective. Guidance computers calculate the required vector changes in milliseconds, translating digital decisions into physical motion with remarkable precision. Another key concept is proportional navigation, a guidance method widely used in interception systems. Rather than aiming directly at a target's current position, the system predicts where the target will be and adjusts its course to intercept that future point. This method minimizes energy loss and maximizes hit probability. Maneuverability ensures the platform can follow these calculated paths, while guidance ensures the calculations remain accurate despite changing conditions. Defensive systems rely on the same principles, often under far tighter time constraints. Interceptors must detect, track, and engage threats within seconds. High maneuverability allows rapid course corrections, while advanced guidance fuses data from multiple sensors to reduce uncertainty. The faster and more precisely these systems can respond, the greater the chance of neutralizing incoming threats. Electronic warfare has added another layer of complexity. Modern guidance systems must operate in contested environments where signals can be jammed, spoofed, or denied. To counter this, designers use sensor fusion, combining data from radar, infrared, optical, and inertial sources. If one sensor is compromised, others can compensate. Maneuverability supports this resilience by enabling alternative flight paths or engagement strategies when ideal conditions are not available. Artificial intelligence and machine learning are beginning to influence guidance logic as well. Instead of relying solely on predefined algorithms, newer systems can adapt their behavior based on observed patterns. They can recognize evasive maneuvers, adjust pursuit strategies, and optimize energy usage dynamically. Maneuverability becomes more effective when guided by systems that learn and adapt rather than simply react. Despite these advances, maneuverability is always a balance. Extreme maneuverability often increases structural stress, reduces range, or raises costs. Designers must decide how much agility is enough for the mission profile. Guidance systems help manage this balance by ensuring maneuvers are purposeful rather than wasteful. Precision reduces the need for constant, aggressive corrections, conserving energy and extending operational reach. Naval and ground-based systems apply the same principles, though in different environments. Sea-skimming weapons rely on precise guidance to maintain altitude just above the surface, using maneuverability to avoid defenses and terrain. Ground-based platforms must account for obstacles, clutter, and complex target environments. In each case, guidance translates environmental awareness into maneuver decisions that keep the system effective. Ultimately, maneuverability and guidance systems represent the fusion of physics and information. One provides the muscle, the other the mind. Neither is truly effective alone. As sensors become more capable and computing power continues to grow, guidance systems will gain even greater influence over how maneuverability is used. Instead of raw agility, the future points toward intelligent maneuvering, where every movement is calculated, justified, and optimized. Understanding these concepts helps explain why modern military technology looks and behaves the way it does. Sleek shapes, complex control systems, and layers of sensors are not design excesses, they are necessities driven by the demand for survivability and precision. Maneuverability allows systems to respond to threats, while guidance ensures those responses lead toward mission success rather than random motion. In the end, the true power of modern systems lies not in speed or firepower alone, but in their ability to think and move as a single integrated whole. Maneuverability gives them freedom, guidance gives them purpose, and together they define the character of warfare in the modern age.